convection zone, and the magnetic field is actually stored below the convection zone, where the flow is also going equatorward, where there is a very strong shear, which can produce very strong magnetic fields. And it is.
And these are charged particles.
Sorry?
These are charged particles, the ones that are rotating with this. Charged particles.
Yes.
I mean, what is what produces a magnetic field?
The magnetic field is generated by, this is of course a fully ionized gas in the solar convection zone. And then the magnetic field can become amplified in the stable layer below the convection zone, where there is shear. So the rotation rate of the interior of the sun changes rapidly when you go deeper down, especially near the base of the convection zone. And furthermore, it is conjectured that the magnetic field in this layer below the convection zone is actually in these magnetic flux tubes, which are sort of very highly concentrated magnetic fields. And the strength of these magnetic fields can be, or has to be, of the order of 100 kilogauss. Whereas on the sunspots, it's a maximum of a few kilogauss. And then the scenario is that when these magnetic flux tubes, when the magnetic field is strong enough, the tubes become unstable, and then they erupt in a dynamical timescale from the base of the convection zone to the surface, thus forming sunspots. So there is no need for a separate theory of how to produce sunspots, because you assume that you have flux tubes at the base of the convection zone, and then they just appear at the surface due to a magnetic buoyancy instability.
But nobody proves that it's possible to generate magnetic field. Yeah.
Yes, exactly. So that's the problem. How do we form such creatures in this layer?
Yeah, that was my question.
Hmm?
That was my question, actually.
Okay, and we actually tried something like this with convection simulations. We took a Cartesian box and then we imposed a shear flow which is somewhat reminiscent of what we have in the sun at the base of the convection zone, and try to see how strong magnetic fields we can get and how actually concentrated they are. And well, you can see the results from this paper, and the gist of the results is that we don't really see very concentrated, strong flux tubes. We do get strong magnetic fields, but they are not quite as strong as what is usually assumed in these flux transport modes. So,
what is the maximum value?
We get something like 5 or 6 times equipartition. But in these models, you need to have maybe 10 times more. Okay.
Isn't there like a Matthias Blanco in his PhD thesis proposed like also something from sunspot from flux?
Yes, there are these things where you can sort of evacuate flux tube with sort of an explosive evacuation of the flux tube, and you get quite strong structures. The problem is how to form these self-consistently without having some very special initial conditions, for example. And this is what we tried here. So, of course, the shear profile was sort of ad hoc, but it was more self-consistent in that sense. Okay, then the most fierce competitor to the flux transport dynamos is what we call the turbulent dynamo, which produces magnetic fields not only below the convection zone, but all over the convection zone. And these fields tend to be much weaker than the ones in the flux transport scenario, And they are also much more diffuse, so they are not concentrated on these very strong flux tubes. And then the problem is that if we can, with this sort of models, if we can reproduce the other main characteristics of the solar dynamo, how do we produce sunspots? Because if we have a very diffuse field, then we have a problem how to form flux concentrations. And what we consider here is that we have turbulence, as we have convection shown, it's very turbulent in the sun. So then we consider an effect which was presented in many papers by Igor and Nathan, where the turbulence has a negative effect on the mean magnetic pressure, which can lead to an instability that can actually form flux concentrations. Okay, then a bit of theory. So let's consider the momentum equation, where we have the momentum stress tensor, which contains Reynolds stress. We have the gas pressure, and then the magnetic pressure, magnetic tension, and then viscous effects. Then we do the usual averaging procedure. We get a very similar equation, but now we have two parts to our momentum stress tensor: the mean part and the fluctuating part. And the fluctuating part here deals with turbulence. And if we don't have any mean magnetic fields, then the fluctuating part of this tensor still contains our Reynolds stresses, and we can have a small-scale dynamo which produces magnetic fields without the mean magnetic field. And then if we do have, in addition to just the fluctuating magnetic fields, we have a mean field, then this fluctuating part consists of two contributions. The one without, the one which is present without a mean magnetic field, and the one where you have a contribution from the mean magnetic field. And this can be parameterized in this way, where we have these betas are unit vectors along the mean magnetic field, and then we have unit vectors here along the gravity. So this is a contribution which appears if you have anisotropic turbulence. And with this sort of parameterization, we can rewrite our Lorentz force, where we have a contribution from the mean magnetic field, and then we have the fluctuating contribution, which is given by this equation, and we can write the whole thing in this manner. And here the coefficients Qi are now functions of the magnetic Reynolds number and the mean magnetic field. And we see that this term here now is representing the mean magnetic pressure, and we see that if this Qp is large enough, then this guy can change sign. And
you said this depends on magnetic Reynolds number. It's just like you have measured this, or like simulation, or is
yes,
analytically
both actually. So theory predicts that it will depend on the magnetic Reynolds number, and we also have results that I will show later on that. Okay, given this parameterization, this modified Lorentz force leads to a large-scale instability. Here I just show the growth rate of this instability. If we first of all consider the case where QB is 0, then we recover the growth rate for the Parker instability, Parker buoyancy instability, which is active if the scale height of the magnetic field is sufficiently less than the scale height of the stratification.
Larger. No, shorter, yeah. Right.
Shorter.
Yeah.
Yeah. And but in the opposite case, this means that in the Parker buoyancy instability case, you have to have some inhomogeneity of the magnetic field for that to work. But
And
now,
this parameter Qp can never be bigger than 1.
it can be bigger than 1.
And then we'll
But
have
then this term has to
change sign.
Yes,
Okay.
and that's exactly the case that we are dealing with here.
Okay, so,
So if QP is
yeah.
larger than 1, then we can have an instability, but
Mhm.
then this HB here can be very large, so we can have an instability even for a uniform field. And this is what we set out to do then, to calculate these coefficients from direct numerical simulations of turbulent convection, and then we compare the results to earlier results from forced turbulence simulations, and we hope this is not doomed from the outset. Okay, so then we have two different convection setups where we solve the usual set of MHD equations, conservation of mass, momentum, energy, and then the induction equation. And we consider two different cases with a weak stratification, where the density varies only about 20% between the top and the bottom, and a highly stratified case where you see that the convection is highly anisotropic, where the stratification is about 320. And
Without shear.
this is without shear, without rotation, only just convection. Okay, maybe that is enough of that. Okay, then maybe I should go back to the equation here. So now we take this equation, and then we impose a uniform magnetic field on our simulation. And then we work out what we get for the stresses, and we end up with a set of equations like this, where the zero now refers to the state where we don't have an imposed magnetic field. We allow for the possibility of a small-scale dynamo, which is usually absent in our simulations. And we perform simulations with different strength for the imposed field and different magnetic Reynolds numbers. And okay, maybe it's best to show the results. So here are our results on the lower row. So what you see here is this is the effective magnetic pressure as a function of the mean magnetic field. And this is now for 4 different cases. These are from earlier papers by Kapyla and collaborators. This is isothermal non-stratified turbulence and isothermal density stratified turbulence, and then here are our results for weakly stratified and strongly stratified convection. And what we see consistently here is that for mean magnetic fields less than the equipartition field, so that the magnetic field energy is less than the kinetic energy, there is a region where the mean magnetic pressure is negative, and it's possible to have this instability.
The magnetic field is horizontal or vertical?
Here it's horizontal. In all of these cases we use a horizontal imposed magnetic field. And
Change when you use different directions of the magnetic field?
yeah, there is a difference between horizontal and vertical. We only do horizontal here. And
What uniform field for oscillating, or
sorry,
which kind of field you have?
this is a uniform field which doesn't change as a function of time. And here we have different sets of points. Each one of these short curves here is one simulation with the weakly stratified case, and we have 4 different magnetic Reynolds numbers. 10 is black, 20 is red, 40 is blue, and then we have yellow with 70 for the magnetic Reynolds number. And we see that okay, it's very difficult to say whether there is a really clear trend here. It might be that for larger magnetic resonance numbers you get a slightly larger effect. And in the strongly stratified case, we don't really have a single value for the magnetic field as a function of depth. That's why we have these sort of long curves here from a single simulation, which do not really overlap quite as nicely as in the density stratified isothermal turbulence case. But still, it seems to be clear that there is an effect, so we get a negative contribution to mean magnetic pressure.
The last bottom figure, different Reynolds number, we have for each value of a magnetic field, we have for some fields, two values of pressure.
Yeah, okay. The problem is that the magnetic field in the simulation is actually not constant. So you have pumping effects, for example, so that the initially uniform field is no longer uniform in the saturated state. And that's why you have these sort of multi-value things here.
Well, another reason is that you are, of course, plotting B average divided by B equivalent, and B equivalent is changing the steps.
Yeah, that's true.
That's why we can get sometimes the entire curve as one run.
Yeah.
And why is that the pressure of the weakly stratified convection is bigger than the strongly stratified?
Yeah, the effect seems to be bigger in the weakly stratified case.
Which is really against our intuition,
Maybe yes.
Why it is
But-
against intuition?
because you need to have high pressure, you have to have big differences.
But this is contribution of turbulence to large-scale magnetic pressure, which is more non-trivial effect.
You mean that here the turbulence is not so big?
It's strongly homogeneous. So the contributions, and we calculate here global contributions. So it's not obvious that in the
It's
strongly
not obvious, but
stratified case.
if you speak about the turbulence, then it's even more strange.
So there's two things. First of all, if you're actually looking at the instability, then you do need strong stratification. So that means if you actually have your mean field model and you have your QP already, you know it already, and you include it, then you will never get an instability if it's not stratified or weakly stratified. You will only get an instability if it's strongly stratified.
I understand.
But then of course you need the QP parameters, and they do exist already in the completely non-stratified situation, as you see from the top left curve.
Yeah.
There's no stratification whatsoever, and already then you have an effect. And quantitatively it looks comparable.
Yeah.
But I mean, yeah.
This is not because the parameter you put are crazy.
Well, we don't think that they are completely crazy. No.
But I mean, is there an obvious reason why it should become weaker for stronger stratification? I mean, these QP parameters,
Here we
they depend on
have
all
strong
kinds of physics.
stratification. We have strong inhomogeneous turbulent convection. So in that case, practically upper part of convective zone doesn't contribute to this effect. Okay, depends on the distribution of turbulent kinetic energy, because we prefer here.
Maybe
No, but
we
you
should-
know, I think, ladies, I'm sorry, but just to finish. There is no stratification at all. Everything is constant. There will be no
Yes.
pressure at all. So how can it be that suddenly you get this big pressure? Okay, but we discuss
No,
this
it's a suppression. So locally, he has the magnetic field.
Yeah.
That suppresses the turbulent pressure, the
Yes.
turbulent RMS velocity,
Yes.
and so you begin to have a local under pressure,
Mhm.
and that corresponds to negative magnetic pressure.
Okay, so you mean
And
that
that
in
can
a
have-
way it's a small thing. That's what you're meaning.
It's
Yeah, the
it's
total-
a small
the total
turbulence,
pressure is
yes,
always
which is
Okay.
suppressed.
I'm sorry, interrupt.
Okay. Okay, so then I have some slides of the. Oh, I'm pressing play on your computer, it seems. Okay, then we have the contribution to magnetic tension. We find that this is, we have always a positive contribution for our three cases here. I didn't show the non-stratified case here, because the data was much more messy. And, okay, maybe this is not so important. Okay, this might be more important. Then we have the final coefficient QG here, which is now the should be present when you have an anisotropic turbulence. And what was found earlier in the forced turbulence case was that it was always consistent with zero, which was surprising, I think, also theoretically, these results. And, but for the convection, we do find actually that there is a mostly positive contribution to QG in the weakly stratified case, and also in the strong stratification. There is actually one run where it's always negative. This is actually points only from within the convection zone. We have cut out the points which we have these overshoot layers above and below, and these are not shown here. So these points here correspond to the points which are close to the border of the convectively unstable layer. And
sorry, what is the difference between set A and set B again? Remind me again.
this is the weakly stratified
Yeah,
case,
yeah, strongly.
and this is the strongly stratified
Yes.
case. Okay, and what we can do now is that we can do mean field modeling. So we average our equations, and we use the coefficients Qi from the DNS or fits to the data, and then we use them in our Lorentz force in the mean field model in order to see if we get instability. And here the stratification is similar to the highly stratified direct numerical simulations, but we consider an isothermal equation of states for simplicity. We don't want to have convection in our mean field model. And we also have two different geometries. We have a cube and a slab. The slab is like the convection simulation we had, so it's like a pizza box. And then we want to compare to previous results and to the actual CNS. Actually, in this case, it is homogeneous.
And why not pumping?
And pumping is also not present in.
But why not? It should be present.
Yeah, it should be present. Yes, I think. Yeah, we did have some single runs where we did include turbulent pumping, but the effect was fairly small.
Okay.
So that's another which falls into this category.
And for the turbulent visibility, you have taken an average value?
Yes, that's right.
Yeah.
And that's maybe also not so bad approximation, because within the convection zone it is actually fairly constant, except very near the boundaries.
Even in the strongly certified case?
Yes, even in that case.
You show that actually in figure 4. This negative effect appears for appears for with magnetic fields that are below the partition value. And then in transport we are so which part of the sum actually has importance?
Yes, but the field that you generate, from which you generate the sunspots, is in this regime. So the instability happens here, and the end result is the sunspot. Where the field can be.
Because in the flux tube modeling, instead you need very high magnetic fields in the region in which you generate the field that can reach the surface of the sun. But here it's the other way around, basically.
Well, I mean, he brings up an important puzzle, perhaps, because you would if this method is supposed to work to form a sunspot, then it should work all the way to equipetition. 2,000 Gauss is already equipetition. Already with the gas pressure. I mean,
Yeah.
with the gas pressure, not even just the turbulence pressure. They're all sort of comparable. So that's the issue. And I think the answer then is that this model as such, but if there is no further modification, like for example radiation transport or any of the other features that might be realistic, you will not get sunspots as yet. But what you will get is what we would call active regions. And already the formation of active regions is, of course, an issue and an unexplained phenomenon.
Yeah.
Would you agree?
And also, I would like to add that this instability is just an initial stage for formation of strong homogeneous magnetic field. Because all theories implies that you have originally non-uniform large-scale field, and then you consider buoyancy. Here, the first example, when it's possible to create a homogeneous magnetic field from originally uniform field. And then, if magnetic field will be homogeneous, then Parker's instability can be excited and continue magnetic buoyancy and continue formation of sunspots.
So in this instability you are forming still horizontal magnetic
Okay,
field.
this instability works also for vertical field and for inclined field. Just as a first step of studies, it was performed for horizontal field. But of course,
And then you observe that the horizontal field gets somehow
yeah.
compressed.
And it's really the mean field. It means averaged over many, many turbulent eddies, not on a scale of one eddy.
But if you look at the depth distribution of this, I mean, if you perform a kind of contribution function for these seeds, where would it be maximum? Close to the surface or?
Yes, you show that probably. You will show that.
Maybe.
And so in some simulations you use isothermal, isothermal gas, but doesn't mean so you didn't just look at the effect by itself. So you don't look how the magnetic pressure, affected the total pressure, because as isothermal they don't connect.
You are talking about the overall stratification of the sun, yeah?
Yeah, I mean, you don't have these. This is right. When you have isothermal gas, you don't let the magnetic pressure don't really interact with the total pressure, with the gas pressure.
No, it does. You have. I mean, first of all, you are talking about perhaps really the overall stratification, and of course you have the overall gas pressure or the total pressure. Sorry, the total pressure. Its gradient must be equal to gravity, regardless of what contributed to this total pressure, whether it's magnetic field or whether it's a mean field magnetic effect or anything.
Okay,
So
it doesn't have to do with.
It has nothing to do with isothermal, so that is still okay. Isothermal is just a special way to describe how the entropy is changing with radius, and it's stably, so it's a stably stratified environment here,
Okay.
so that we don't have yet another instability to worry about at the same time.
Okay. So here are some results for growth rate. We do find an instability in the mean fields models, and this is now the growth rate of the instability as a function of the imposed magnetic field strength for the two different geometries, and the slab geometry here corresponds to our DNS, and we see that it increases, and it is a maximum of about 0.25 equipartition field strength. And what we see, walk up again. What we see in this geometry is that we do have we have these magnetic structures forming quite near the surface, and there's actually quite a number of those.
Which component? Horizontal? Yeah.
Yeah, this is the horizontal field. I can't remember which one it was,
Yeah, okay.
but it doesn't matter.
I think so
Yeah.
too.
Yeah, y direction.
Yeah, yeah.
Yeah.
It's in the direction of the mean field.
Yes.
Right. So what you would see is latitude somehow.
Right, yeah. And why I say that this is a high wave number thing here, because you count how many things we have here, then you compare how many convection cells we have in the same in the corresponding simulation. We see that actually there's fewer convection cells than we have in these magnetic structures. So that's kind of a discrepancy between what we would expect to see in a simulation and what we actually see in the mean field calculation. Another thing is that if we believe what the saturation strength of these structures in the mean field model is, this is now the solid line here corresponds exactly to the geometry we have in the simulations. We see that it's below 0.1 equipartition, which is fairly low. Even compared, this was done for the fastest growing B naught, which was 0.25 equipartition.
But that's an average over the entire mean field domain.
Yeah, that's an average.
So the maximum in the mean field model is already probably more.
Yeah, that can be more. And okay, here we see that if we increase the box size in the x direction, then we increase also our growth rate of the instability and also some of the saturation strength. Now the question, of course, is that we do see the instability in mean field models. Do we see it in direct numerical simulations? And the answer is that at least no clear signs have been seen so far. And if we believe this is now a simulation, a direct simulation corresponding to imposed field of 0.3 times equipartition, which is where the mean field calculations indicate that we should have a maximum growth rate. This is the x component of the magnetic field, and we have an imposed field in the x direction.
And this is strong, strongest.
This is strongest certified case.
Balancing the DNS.
No, here there is.
That we haven't
Here
done.
there's no constant.
I mean, then it wouldn't be DNS.
Side disturbance between.
Yeah, but you will have
Otherwise, you will have
no clear effect of the instability.
Yeah, then you should have an
So
institution.
the mean field model should be made more
It's
accurate.
very important to have separation of
Side over
scales.
side.
So
Yes, and this is actually one of the issues that we might have with the DNS. We don't have a proper scale separation. And we could also be at a too low magnetic Reynolds number still with the DNS.
What kind of range
Here we had 50 in this case. In our units, which are a factor of 2 pi smaller than the commonly used units. And okay, this was actually the last slide I had. So I had some conclusions. So we do find a negative contribution to mean magnetic pressure in various different DNS settings. And we do find an instability also if we put these coefficients into a mean field model. But direct simulations don't really show clear signs of this instability. And future work is that we plan to consider also vertical fields in the future to see how this affects the results.
Thank you. Yeah, Frank?
As you know, convection changes character rather much if you go along the main sequence from early F stars and down to M, and also if you go vertically in the HR diagram up to subgiants and giants. And there are lots of observations coming concerning spots for these various sorts of stars. My question is whether you can make a prediction where you expect spots to be particularly rich in the HR diagram, because that could be very nice to have, you know, and if you turn out to be right. It would be very good.
That's a very good question. Something we haven't really thought about.
But I mean, magnetic activity does not just change along the HR diagram, but it does depend on the inverse Rossby number. And so there we have, of course, certain knowledge about how that all changes.
Have been observed this in other stars?
Sunspots or spots have been observed in other stars, yes. And the most prominent examples are those where the field is fairly strong, and then the spots are very big. There's no observation yet of a spot which has the size of a solar sunspot.
Yeah, these are stars which rotate much more rapidly. And so
Yes,
and the
yes,
spots are
3-day
closer to
rotation period.
But for solar cap stars now, with the Kapyla being up, we get lots of this kind of information.
Most, yeah, right.
At least for stars with considerable activity.
Yeah.
Because as you put it, there should be a star where the magnetic field is completely different to this other magnetic. You mentioned supergiant, didn't you?
And that's a different family.
Yeah.
But
No, I mean that it would be very interesting to compare these.
Indeed.
Yes.
Does it make any difference when you look at the reduction in pressure, if it is along the magnetic field or perpendicular to the magnetic field? When you look at how much the point is that you are taking turbulent energy, which provides turbulent pressure. You are putting into magnetic energy, which gives you magnetic pressure. And the point is that the relation between energy and pressure for the magnetic component is different than for the turbulent component. The 2/3 in one case and in the other is equal for 1/3 to 2, depending on the.
So there is, of course, two contributions. There's one which has to do with delta ij times qp, which is a function of the modulus of b, independent of the direction. And there's the other component, which is bi bj, multiplied by yet another function, which is called qs, which itself depends on the modulus of the magnetic field. So this is independent of the direction.
Okay.
The directional information comes in through this, like here and here. And it's and the mean field. And so then, what the direction of the magnetic field really does depend on, or you will see, of course, when you solve the mean field model. And what Kapyla has shown, remember this picture towards the end showed that you find a segregation of the mean magnetic field in the direction perpendicular to the imposed field or to the large-scale field. The large-scale field was into the plane, and the field was uniform along that imposed direction. There was at least no instability in this direction, and only perpendicular. We know of some calculations where the magnetic field can actually also break up in this direction, but that, as Kuhn has now shown, happens only for stronger magnetic fields, and might actually also be of importance. I've not studied that further yet. But in principle, the instability can be three-dimensional. But at onset, it's a two-dimensional instability, as we have seen so far. That you may not have noticed yet. Did you know that? No.
About?
That the instability, so there is an instability also in the direction into the plane.
Yes.
But it happens at stronger field strengths, as Kuhn has.
Yeah, there's other wind for instability.
Yes. Matthias has a question.
Yeah, the mean component here, obviously, it acts on z dependencies. So, was then the average used for calculating the Q coefficients just a y average, or what was it?
No, that was a horizontal average, actually.
An x and y average?
Yes.
So that's not consistent with the mean field model. But here's a different average, obviously.
But also performed for forced turbulence, it was performed other kind of average and obtained the same results.
No, but I mean, I think you are eventually bringing up the question of finite scale separation, and that is a problem that, of course, we are concerned about for a long time, and you mentioned this in the conclusions. So if the magnetic field itself isn't actually uniform, and of course the mean field result shows that it's not uniform, then that fact is likely to suppress the efficiency of this QP parameter. The QP parameter may become wavelength dependent, as we know for all the other turbulent transport coefficients. And how much that dependence is, we have not looked at yet. And it would clearly be very concerned about that. And that might be, of course, the reason why we have not seen this effect in direct simulations yet. And then if that's the case, we know, of course, also how to circumvent it. But then we just have to make the box big enough, or we rather tune otherwise certain parameters so that we understand when we should see it and when we should not see it.
And when you have shown the dispersion relation for the stability, so this will seem to me to be derived from the ideal setup, so without the diffusivity.
Yes.
Is correct. So what is the influence of diffusivity if you would include them?
Okay, it's probably just a minus.
Just you need to enter this one thing.
Probably just a minus k squared times eta effective. Actually, we know this from the mean field calculation already.
Are those contributions relevant for the mean field model? Or
Yeah, eventually, yes.
Yeah.
So that leads to, so therefore, if the diffusivity becomes big enough, then eventually the diffusion and this balances each other. Yeah, that's correct.
So there should be an influence of the quenching of the diffusivities. It is not included in the mean field model, is it? Or no.
No, but then likewise, of course, this QP is also being quenched.
Yeah, of course.
So we,
Yes.
a lot of things need to be done, yes? Gustavo?
In the going back to the scale separation, if you do the forced turbulence, then you have better scale separation between scales, so you see better effect.
Yes, actually the latest simulations where I was looking at a movie, producing a movie just last night for the front level of 1/8 run, which you have not even seen. That one shows actually big patches at the top. It's the first time that I actually see that. And of course the open question is, what is that caused by? Is that actually caused by this? But of course, if we really want to address this question, we need to look further into the simulation and not resubmit today, maybe, as we were originally planning. Yes. Yeah.
So you get different result if you have a strong imposed magnetic field, right? So you have a homogeneous isotropic forcing. So my question is it an effect of the, is it just an effect of the magnetic field, or is it an effect on the isotropicity of the turbulence? So if you can make the turbulence high and isotropic without enforcing a strong magnetic field to begin with, you get the suppression effect.
Yeah.
So it's only a province of the level of isotropicity of the turbulence.
Yeah. We'll have
So the fix
in the case of stronger isotropic turbulence,
So if you do that with, for example, strong stratification, that's
yes, strong stratification.
This one?
Yeah. So any additional anisotropy would be described through this guy here. And so Petri simulations show actually quite clearly that this QG is positive.
no, but even if the average is zero, right?
Which average is zero? This one?
No, so is this average square or b square average?
This is the average squared.
Okay, so if b average is zero, but you do have strongly anisotropic turbulence for other reasons,
No effect.
you will have no effect.
No effect. We need large scale phase. Because all the effect is the effect of small scale turbulence to the large scale magnetic pressure. If mean magnetic field equals zero, no effect. Of course. But
why not?
I mean, where should the field come
maybe I
from?
will
You think
explain.
of the turbulent field should be.
Could I explain this?
Yeah.
Yes, I think you can discuss
Is
that.
there any other question
Okay.
to Petri before he comes up? We have still a little bit of time because I should tell those people that there's a talk in the program on predictability and simulation by Jenny Nilsson today in 13 minutes, and that is about modeling of the Mediterranean Sea, predictability of Mediterranean conditions. Ocean. I think it's the ocean. It's the ocean, but
Slowly bold.
yes, right. Okay, so
Yeah, I would like to explain physics of this effect. So what we have here, we have small scale turbulence or small scale turbulent convection. So there is a contribution to total pressure. There is a contribution of turbulence. Of course, we have gas pressure, and we have large-scale field, so we have contribution of regular magnetic pressure. Okay?
But why don't you have-
And
why
all
don't you
the
have
sorry.
Why don't you have the contribution from the small scale field?
Yes, this is a contribution from the small scale. I just would like. Yeah, this is just.
Okay.
But now you're saying if that was anisotropic, what would that
Yeah, I would like to answer to your question also. So, what is the total turbulent pressure? If we, let's consider, for simplicity, isotropic turbulence. Then we have the total turbulent pressure, 1/3 of magnetic energy density plus 2/3 of kinetic energy. Okay? So this is a classical result, and if we have a field, there is 1/3 of magnetic energy. Okay, this is a total pressure. So the total contribution of magnetic and velocity fluctuations. And if magnetic field is uniform, then sum of turbulent kinetic energy plus turbulent magnetic energy is constant. Okay? So if it is constant, then just yes. So what we have? 1/3 of magnetic energy plus 2/3 of magnetic. Let us add 1/3 of magnetic energy and extract 1/3 of magnetic energy. Okay? So since this value is constant, so variations of turbulent pressure equals minus 1/3 of change of magnetic energy. So if we generate magnetic fluctuations, turbulent pressure decreases. And this is the essence of the effect. This is the reason why we have negative contribution of turbulence to the total magnetic pressure. Of course, if we have anisotropic turbulence, strong anisotropic turbulence, then we change only here coefficients. It will be, instead of 1/3, it will be 1. So it will be much larger depression of turbulent pressure.
Independent of the direction, yeah?
But-
Is that means
yeah.
magnetic,
But of course-
small scale magnetic field is mostly horizontal or vertical?
Yeah, we're speaking about the small scale, yeah.
Yeah, but in which direction?
Hmm?
Is the direction important?
Uh,
Or is simply just that if there is there, maybe it's completely unimportant whether it's up or down? I mean, horizontal or vertical? I think so. It just means that the fluctuations are mostly one-dimensional.
yeah.
Then you have a...
But in principle, fluctuations, when we consider fluctuations, even if mean magnetic field equals 0, we have small scale dynamo generation, then there is a decrease of turbulent pressure. But so we have addition to the total pressure. So since this value is decreases, so we can extract from here the quantity which depends on the mean magnetic field. This is this quantity. And plus regular mean magnetic pressure. So we have negative contribution of turbulence, and that's why we have 1 minus QP. And QP describes all contributions of turbulence.
Yes, but
Yes.
but if we all of what you say before, right?
Sorry?
But what happened if the mean magnetic field is 0?
Okay, if mean magnetic field is 0, we don't have this effect because we
No, you still have that effect because all that you say
we have
before-
effect. Okay, we have effect of decreasing of turbulent pressure, but we discussing what is the large scale manifestation of turbulence,
No, but you
small scale turbulence.
you still have a drop in total pressure.
We
right?
have, yeah, but very important that total pressure is always positive. This is all effects are very
I
different.
don't understand
Gas
what you're
pressure is
saying.
much larger than turbulence.
I mean, it's true that this can become negative.
No, what I'm saying is
It does not
that
help if
that
this
kind
is
of factorization makes sense only if B average is different from 0.
Yes. All this
This
effect.
is valid even if it's 0.
But the drop in pressure exists also if the mean magnetic field is 0.
Of course.
Yeah, of course,
But,
yeah.
but of course it doesn't help because it's just a coefficient in front
Yeah.
of this.
Yeah, but if you write it that way, I will get that there is no drop in if I write P top as you write at the bottom, okay? If B average is 0,
Yeah.
I will get that P top has not changed. Right?
It's just this.
It's just P and P is
Yeah.
This is not change.
Correct.
This is P. This is
true.
the
Because
sum
if
of
I look
gas
at the
pressure
machine-
plus turbulence pressure.
What is the zero on top?
Sorry?
What is that zero on top?
That means that's immediately
With zero mean magnetic field. So this is gas pressure plus turbulence with zero mean magnetic field, which includes turbulent kinetic energy
Okay.
plus a small scale dynamo fluctuation. Okay, but all these effects are important, very important for when we have non-zero large scale magnetic field. All these effects which we discussed here are important when we have non-zero mean large
Why
scale.
you say that? I don't know.
Because we would like to study instability of the large-scale field, not instability of the turbulence. We study here effect of small-scale turbulence to the large-scale magnetic pressure.
I mean, in other words, suppose you do a simulation, and you are not resolving all the small-scale eddies in your accretion disk. Then you have, and you use just simply equations which are the mean velocity, which you resolve. Then what we are saying is that if there are this smaller scale turbulence, that certainly does exist, that leads to additional terms. One of them is turbulent diffusion. And that is something which many people take into account without thinking that this is something non-trivial. And what we are saying is, at the same time when turbulent diffusion enters, there's all kinds of other effects that enter. One of them is the lambda effect, which leads to a differential rotation of the sun. Many people don't know about that. For example, in laboratory flows, they think, okay, there's turbulent diffusion, and now there's something else happening just because of rotation, which is something new, undiscovered. That's not correct. It is a lambda effect. It's certainly also there. And now we are saying, in addition to terms that have to do with the mean velocity field and its gradients, which is turbulent diffusion, there are also terms which have to do with the mean magnetic field in the momentum equation. And these are these effects. So if you are not resolving the small scale flow, you would really do something wrong by not thinking about this, not taking this into account. You can always say, I don't care about this, and then you must solve simply for large Reynolds numbers. And if you do this
I'm
at
not
small
saying
Reynolds
that I
numbers,
don't care, but the reduction in total pressure is there even if there is no mean field.
Sure. But of course, then you talk about inhomogeneity of the little b squared. Of course, if that's varying, that's completely clear.
Yes.
I mean, of course, if this one is non-uniform, then it's of course non-uniform. But it's the question is, can you induce a non-uniformity of this total pressure by the mean magnetic field? If that's the question you are asking, you must allow for this mean magnetic field to be there. Or otherwise you must address what should cause a non-uniformity all of a sudden in horizontal direction. Why should there be all of a sudden a low pressure at 45-degree latitude? And of course, one good reason is that there's a weak mean magnetic field. Then we are saying there's actually a decrease of pressure.
No, but what I was thinking is that if you could induce variation in the turbulence pressure with stratification, for example.
Yeah, but not in the horizontal direction. There's no way that you can get a pattern. Right. So, any other questions? If that's not the case, then we are in good time for going over to the other building for those of you who are interested in the Mediterranean modeling of the climate system in the ocean. All right then. Thanks, Patrick. There's a talk, of course, on Friday, in 2 days' time, at the university by Ralph Keeling about the CO2. His father is very famous through his measurements of CO2 in the atmosphere, the Earth's atmosphere, since the 50s. It was the movie by Al Gore. Then Al Gore mentions his father. So he's speaking in the Aula Magna at 1 o'clock on Friday. And after that we have a barbecue here at Norida.
For whom?
For whom? For everybody. So if you
No, I will not be able to.
if you see us out on the road, you're welcome.
But Alex, let me ask you.
Yes.
Something like this. I can mention that in that equation which I found is a nice origination or
He gets this, yes. Where is he? He's here.
Extremely good Chinese.
Right, okay. And he is a student, yes?
For example, strong rotation.
I see what you mean, yes, yes.
You can
Then
develop
we have,
he can come here.
it will be, if we have
We should talk to him, yes. I mean, I should, you
I
should
can
introduce
use
him to him.
I can send it to you, or we can together and see the curriculum.
Yes, yeah. Maybe it's
You will not be disappointed. You will walk
Okay, yeah.
the change
And the important thing, he can how much he
change
has
of
contaminated.
Yeah.
His vision.
Yeah.
Very good.
So, and how, when did he start his PhD, or when does he want to finish it?
He finished it. Now because
It's
the
postdoc,
exam
yeah?
road.
He's a postdoc now, yeah? Yeah, right, on my grant, I am basically
When you have
running
energy, the turbulence,
I might get a new
the same energy, the magnetic
my current grant,
Yes,
support
because
the
it's
postdocs.
too-
But I do have postdocs with knowledge, of course.
Yeah, but it's not the whole, only half, because we want to help him.
Connect plus magnetic.
Anyway, we should maybe talk to him.
But
Next week.
you have, for
And then
example,
I should also know what,
No,
so
I-
you
I-
are employing him at the moment, right? You are employing him at the
very
moment, right?
structured.
Yes, okay.
We want to take him in the future also.
Yes, okay.
We would like to have
Uniform
yes.
I mean,
Then instead of doing 1/3,
Yes,
it
yes,
should
okay.
be 2, right?
So,
which is very interesting.
please
The
let me
relation
know the
between the
details
magnetic
about your
pressure
postdoc.
and
You
the
can email me about that.
Yeah, what he's looking at, but within nutraphysics.
No, I should go.
magnetic
Yeah,
pressure
yeah,
is
okay,
V
thank you.
square half. So
In order to, okay.
in that case, what I was trying to understand, your